And it's now time for the second part of the presentation, and that is about graphics. So who of you does something with the pixels on Pebble screen? Okay, I think most of you, if not all. And we will show you a few details about how to improve that. But first, similar to the memory layout and all the limitations we sketched out there, we have limitations on the display as well. Well, most notably, we have a black and white display. And whenever you show the Pebble to other people, they always say, well, it's only black and white. Yes, well, that's true. You cannot do any gray on that, but we show you how to do that. And also, 144 pixels, well, that's not much. But if you think about it, the screen isn't large either. So you are essentially running at 175 dots per inch, which is a lot. And depending on your vision, you can distinguish individual pixels or you cannot. And then also, when I first read about the Pebble and kickstarted that, I was so excited. I thought, well, an e-paper display, how fast can that be? I thought of a Kindle, and that takes more than a second to refresh the screen. And the first thing I did when I got my hands on a Pebble was to do some graphic effects to see how fast it can go. And I easily achieved 30 frames per second. I mean, I didn't measure that precisely, but we can certainly get 25 frames per second. In fact, hardware-wise, there's a refresh rate of 27 milliseconds. And it's super fast, and you can do that. And I think there are too few applications out there right now that do fancy animation. And we teach you how to do that. OK. And it's, again, the double click. So the structure of that talk is first, Matt will tell you how the pixels will actually end up on the physical display. And after that, we talk about dithering. And then with 2.6, we introduced a new API to give you direct access to the frame buffer. So you can do super smooth and super fast animations. And we explore that a bit more. OK, let's start with the pixels journey.
Great, thank you. So we're just going to talk very quickly about the layer stack. For us, everything in our more basic drawing libraries is layers. You can either draw using layers, which are similar to widgets in other programming paradigms, or you can use direct pixel drawing like gpath, draw pixel, draw line. So the way that layers work is that they're actually stacked on top of each other. We start by adding them to the window layer, and then we just keep on stacking them on top of each other. When we render them, we're always rendering them from back to front. So each, like the background image would render, then the text layer, and then the time layer. How this works under the hood is that once we've rendered everything to our application frame buffer, we want to actually see it on the display. Some applications aren't full screen. A lot of times it's nice if you just have the time done for you on top of the screen, and you can create a non-full screen application. Your resolution is going to be 144 by 152. So you can see over here, the application frame buffer is missing that top bar, that top space. The system compositor is going to render that into its own space. So our application isn't doing it. We're not like overloading one of your functions and drawing it in your space. So what happens is the system compositor is going to copy the application frame buffer from your space when you're all done rendering those dirty frames that we had here. It's going to copy it into the compositor, and it's going to mix them into the final display. And so this is basically just how we give you your own drawing space, and then we keep the system space separate. So you can imagine we could do other things with this, like overlays or partial drawing patterns to have a combined output.
So as you can see, it's not that complicated at all. In the end, the way we structured our windows, windows have layers, and each layer has its own update proc. And you can create a new layer and set a custom update procedure on that layer. In fact, when you deal with text layers or any other, like a bitmap layer, they are having their own update procedure under the hood. It's not that they're doing any magic there. It's just that they have an update procedure to render their content. The clue here is that you have a graphics context in your update proc, and that is the gate to the actual pixels. All the graphics libraries we provide rely on that graphics context. And we provide different functions here. And if you look at the well-documented APIs, we have, for example, draw text and draw bitmap. This is a direct equivalent to the layers I mentioned earlier. So you can write your own layer, your own text layer if you want to, and just do what the built-in text layer does. But you can also go beyond that. We have other graphic functions, and some of them are dealing with vectors, and others are dealing with raster graphics, pixels. The difference here is that you can easily scale vectors, and the other one is you have more control over actual pixels. Now, what are visuals if they are not animated? We have two different concepts on Pebble, and that is, first, you can have timers. So the way that goes is you schedule a timer at a decent rate, say 20 times per second, and each time you mark your layer dirty, so its update procedure will be called, and then you do something which will result in an animation. And the other one is using properties or, animations or property animations, where essentially you can do something similar, but you would rather call setters of your layer functions in order to make it dirty, which will trigger the update procedure. Either way is fine. If you use animations, you can easily achieve something like easing. If you use timers, you have more fine control and can do whatever you want. So only based on that API that has been there forever, you can achieve some pretty neat effects. So what you see here is an application that is a companion to an iPhone application which directs you to a point of interest. It uses the Compass API, and it uses the same mechanics, the same physics feel the Compass application uses, and you find that on GitHub if you want to. But it uses also drawings to change its state, to give you transitions between different states. And also it scales vector graphics. So that arrow here you see at the top will scale according to the content and the state of the application. All that is just implemented with property animations, GPath, and everything you saw before. There's no black magic here. It's really just the SDK you have at hand. Yeah. It uses vector graphics here, since if you did that with bitmaps, you would see all the artifacts due to scaling and rotation. Vectors here are way better to deal, but I mean, we are not talking about vectors in that presentation. It's all about raster graphics. But that was just a reminder what you can already achieve with what you see here. We are dealing with raster graphics and, to be precise, advanced raster graphics. So, and to do so, we are now looking at two functions that had recently been introduced. And to be honest, there's a third one, but this is only to check the current state of the frame buffer. So the frame buffer, Matt already introduced, is where the actual pixels live. And these two functions will give you direct access to it. So that is that. And then we will do dithering at runtime. And, well, what is dithering anyway? Can anybody explain that? So who has not heard about dithering before? Okay, that's only a few. Who else wants to explain what dithering is? Okay, so the problem we have is we only have limited colors on Pebble, right? We have two of them, black and white. But the real world has plenty of them. So what do? We do the same as Microsoft did back in the 90s. So who's old enough to remember that screen here? Okay, after you put in the 11th floppy disk into your drive, you will have that screen here. And you got that nice gradient of blue here. What do you think? How many colors are there on the screen? How many shades of blue? I see two. Who says more or less? Two. Yeah, actually, it is one. No, actually, it's two. It's an SVGA standard graphics mode that features a 16-color palette, including 2 shades of blue. And at the very bottom, you have a black color. And then if you look closely, you see a pattern. And that is what's called ordered dithering. But in fact, it's just adding noise between the 2 shades of blue, so you won't really recognize that you're only dealing with a limited set of colors. Okay, so I was looking that up on Wikipedia, and I was a bit surprised then. Dithering in general means that you just add some random noise of it to cheat your eye. And that's actually it. That one here is a gradient going from the left to right, from white to black, and it uses 256 colors. Personally, I would bet that Keynote under the hood already does some dithering for us, but assume that you have a full range of colors here. Now, when you reduce the color palette to only 16 shades of gray, you will see distinguishable colors. And this is how it would look like. Oh man. Okay, at least here in that range here, you will see discrete bars of gray, since you only have 16 of them. So what I did as an experiment is I just added random noise to the pixels, right? Just any arbitrary random values. And what I get up with is that one here. It looks perfectly like a gray gradient. And then also I used the other technique called order dithering, and then on that beamer here, at that resolution, you cannot see any difference at all. So just by dithering, you get a pretty decent result. Now, this is 16 shades of gray. We only have black and white, right? So how does that look like? So when I go from white to black, and when I do nothing but finding the closest shade of gray, which is black or white, how does it look like? Well, actually, it's two colors, white and black, okay? And you can clearly see bands of similar color here. Okay, let's do then some random noise. This is how it would look like. And now I use the ordered dithering. And yes, you can still see different shades here. But remember, we are not dealing with 16 colors. We are only dealing with 2 colors, right? It already looks a bit like a real gradient. Now, we are dealing here with 1,680 pixels, which are downscaled for the beamer to 1024. But in the end, there's way more pixels than we have on Pebble. On Pebble, dithering can accomplish quite amazing results. So here is an original color image, and I reduced that to black and white only. And also, I use order dithering compared to a diffuse dithering algorithm that's pretty prominent called Floyd-Steinberg. Now, if you see that on the original size, here and there, it's pretty decent. It's only black and white, remember that. But since it's so far away, or here actually since the beamer scales it down, which is more or less being far away from the display, you have the perception of a gray image. And that is dithering. Okay, so now if you see those two pictures, what do you think is the best algorithm? Right, Floyd-Steinberg? Okay. So just by looking at that picture, I'd say yes. If I look here on the bottom one, I would say, not really distinguishable, but clearly they are. Now, let's look how it's actually implemented under the hood. If you see Floyd-Steinberg, it's pretty simple, actually. You go over all the pixels, row by row, and then from the left to the right over each pixel. And then you find the closest color, which in our case is only black or white. And you calculate the error. So reducing the amount of colors is called quantization. And so I store the error of the quantization effect here by just subtracting the two values. So how different is the actual color from that one I have at hand? And now I distribute that arrow down to the remaining pixels, down to the row below and down to the pixel to the right. And I do that for efficiency, so the algorithm can just go from the left to the right and won't override itself again. But you always only have to look at the one right to you and the next scan line. That also means you have to store somewhere in memory the state. You have to store the full scan line in order to perform that algorithm. And then you do some math. That are just some magic numbers Floyd and Steinberg came up with, and then you apply that, and whenever you hit then that final pixel, you will have the already modified color value and do the same. So that's the algorithm. Compared to order dithering, which is way simpler. Well, yes, there's a matrix, but in the end, the algorithm is pretty simple. As I said before, you can just add random noise to your pixels. And instead of adding random noise, order dithering looks up the random value in a table, in a two-dimensional table called a matrix, where you just put in the x and y coordinate to find the random value to add. And that's it. And if you think about it, It can be parallelized. It doesn't affect any other pixels, and it's way faster to implement. That one is, so whenever you want to learn more about dithering, go to that website here. It's by Joel, I don't know. No, seriously, I try again. It's Lilumas, and that is just, it's awesome. That page just tells you so much about dithering, different strategies, quantization in general. It's just impressive. So what he did is he took a image out of a PlayStation game, and that is a cutscene out of that game here, and he reduced the amount of colors to only 12 colors. So that's that one here. You will see the color palette here below. That's the image. I go back now to the original and back to the 12 colors. That's without any dithering. That's just the closest color out of the chosen palette. Now, that's Floyd Steinberg. Looks way better. It's again only the 12 colors, but it looks way better due to the dithering. If you look closely, I put a white pixel at the top left. Now, when I animate that pixel, you'll see that the whole image will be changed due to the algorithm's nature. The error that pixel will cause will propagate down to the next row and to the next row. And since it's a real triangle, it affects all the left half of the picture in the end. And you clearly see, once you have animation, not stills, but animations, you will see noise that animates as well. And that is absolutely a problem. When you do the other algorithm I prepared before, it's only a local effect there. Whereas here, and other algorithms as well, you will have, as soon as you have animations, real problems. I know that a few applications out there use Floyd Steinberg dithering. John, for example, for his Pebble Snap. There it's not a problem, since he only updates the screen once per second or something. People don't notice it. But as soon as you deal with real animations, you will see it. OK, so that's the bare theory behind dithering in general, and then ordered dithering versus diffuse dithering based on Floyd Steinberg. And now, again, some tooling from Matt.
Great. So I've had a lot of fun making watch faces on the Pebble. And when I discovered how nice dithering looked on the Pebble, I started making pretty much all my watch faces and apps have these additional dithered shades of gray. While working on some different image applications, I found that on the Pebble's display, the one pattern that you can barely discern, and most people can't discern it at all, is the gray 50-50, where it's dithered, it's every other pixel is black or white, a lot like a checkerboard or chessboard for we back there. So when I'm creating these images, I'm pre-generating them on the computer, so I can either use something like Photoshop or GIMP, or I can use some scripts. So first, I'm just going to run you through a quick example of how I'd make a watch face with some cool images. I'm going to resize the image, convert to grayscale, modify the brightness. We'll go through all these together. But this is basically my normal process of taking an image and putting it on the Pebble using the GIMP. So here we open up this cool robot picture from Open Game Art, Creative Commons. And I want to make it into a watch face. So first, I'm going to click on Image, Scale Image, and make it fit smaller than the Pebble screen or the same size. So here it's 144 by 164, because it's keeping the aspect ratio. And they have these options, interpolation. That's how it's going to scale it down for you. The worst option is linear. It's going to look really blocky. It's going to look pretty bad. Lexos, or sync, is a very nice resizing filter. It's going to keep the image very crisp and nice at a smaller size. So there you can see we've resized the image down. Next, we're going to convert it from color to grayscale. So we're clicking on Mode, Grayscale. And so now the image in the background is grayscale. And we're going to just hop ahead. And now we want to start getting it ready so that we can have less than 8 bits of grayscale. We want to just have 3 colors, black, white, and the 50-50 gray. So I'm going to adjust the brightness and contrast to the point where I think I kind of like where the image is looking at, where as you slide contrast to the right in a grayscale, you're actually dropping colors. So if you slide all the way to the right, with contrast, if I end up all the way over here, the image will be just black and white. The nice thing is that I can slide this brightness, which will look at the original values and decide where on the line do they sit. Do they sit on the high end or the low end for the colors? And so you can see the background there, that's after the operation of the contrast. We've got some nice grays sticking out and then some nice whites, and then everything else is black. So we're getting pretty close, but we can still tell that there's more than one shade of gray. There's some darker grays in there. So I'm going to go to colors and posterize. Posterize is going to basically limit us to a certain number of colors. It'll just reduce everything else and just make decisions on does it lie in the black side of the line, white side of the line, or the other number of colors we have. So here I'm going to set the number to 3. So it's going to be under 33% black, 33 to 66 is gray, and then everything above 66 is white. And that's a final image. So now you can see that we have white, the one shade of gray, and black. Finally, we need to actually prepare it for the Pebble. So right now, this is actually a grayscale image. So we're going to go back to image mode and click on indexed. And we're going to tell it, use a black and white palette, 1 bit. We want this to be just like the Pebble's bitmap images. But down here, like Heiko was talking about, we're going to choose how we dither. You can choose some of the other filters he was talking about, like the Floyd-Steinberg, but that's going to be kind of noisy, and you'll see patterns in your final images. If we pick positioned, and it's that one shade of gray, it's going to just look like gray. So then we have the final image. So you can see here we have white, we have a dithered gray, and we have black. And then we scale that down to the Pebble. It looks rather nice. There's another way we can go about it, rather than doing this all in the GIMP, is if you have a lot of images or if you have a web source, we can script it. So I'm here using my favorite tool, ImageMagick, and I'm taking the original PNGs, which are on the left here. I'm telling it to adaptive resize it. That's using that nicer sync or Lanczos resizing filter. The little caret on the right, the greater than, is saying only resize it if it's greater than that size. So if I've got a small icon, that's 3232, it's not going to resize it larger. This next line, the fill opaque, none, it's saying that any color that's none, which is typically your alpha channel, your transparent in a PNG, we want to fill it with FFFF00, which is going to be white. You can make that all zeros, you could also fill it with black. We're going to, once again, change it to grayscale with the color space of gray. We're going to set the thresholds ourselves. And this is kind of nice. This is what we are doing in the GIMP with the sliding bars for contrast, is we're trying to make things settle to good positions. So here we're basically just saying on these images, above that's white, below that's black, in the middle is going to be other. We're choosing an ordered dither pattern of 2 by 1, which means that we can only do 1 gray. It's just going to be the one checkerboard pattern. So in your matrix, it's going to be a 2 by 1 matrix. We're going to tell ImageMagick 2 colors, depth of 1, and then all these last 3 things, these are just to make sure that the PNG is rather small. So if we're using my PNG demo library, it's going to be the smallest size because we're going to compress it pretty high. We're using a good strategy, and we're removing all of the metadata that we don't care about, like when was the picture taken, who took it, was it modified by Photoshop or ImageMagick or from some random website. And we're going to output the new file. You can see here, this one I converted over just to black and white. This one I did the dithered gray. And so combining all those things, I have an animated watch face here that's using animated PNG, a dithered gray, using ImageMagick to script everything. And because it's APNG, it's only storing the difference from one frame to the next. So it ends up being 200 frames. So the animation ends up being 20 seconds long. The other nice thing is that even though we're loading resources from Flash, which typically Flash is slow, because they're compressed, we're reading less, so it ends up being faster per image. So in this case, I'm doing it at 10 frames per second, because it's a rather nice lengthy animation, but you can go much higher. It seems to work pretty well around like 20, 25. It seems to be the max for me. Scaling that up, we can see what the dithering pattern looks like in the animation. So you see on the left, that's more how your watch would display. On the right, this would be the actual pattern if we could scale it up. So you can actually see the dithered checkerboard we were talking about. I'm a big fan of this. I always call it the perfect gray on the Pebble, because to the discerning eye, It's just gray, or the non-discerning eye, however that works. And cool. And then over to Heiko.
You always do the cool stuff. Okay. So is my mic on? Can you hear me in the back? Yep. Okay, cool. So that was all offline, right? Mm-hmm. You use GIMP or ImageMagick or anything to calculate images, and then you load them on Pebble. What I'm going to talk about now is to do that at runtime on your Pebble itself. Well, we cross-compile GIMP, it's C, right? And then we run it on Pebble. No, obviously not. So another thing I want to talk about now is real animations and movements. So far, we were talking about, and that was the animated watch face, changing pixels that are not moving. But what if you have a perfect shade of gray, 50%, moving left to right with the different algorithms? So here at the top, I would use the pre-dithered, offline pre-dithered bitmap as Matt mentioned it. And then also a pre-dithered by Floyd Steinberg, which obviously has some noise on it, also moving that image. And on the lower row, I'm doing dithering live on Pebble. And it's really hard to see the flicker effect I'm going to talk about, especially since we are here on the beamer. So I'm not sure if you can see that. But if you try to see that, start here at the bottom. If you look at the point here, you see that the actual pattern will remain stable while the object moves. And then if you look at the top two rows, you see some flicker already, since the pixels are moving. And then when you have a checkerboard pattern and you move it by 1 pixel, all the pixels that had been white before are now black, and all the black ones turn white until you move another pixel when everything changes again. And that's noticeable and super annoying when you do animations. And since it's so poor to see here, I did that again enlarged so you can really see that. Just look at the the yellow stripe. And now when I move the pre-dithered pattern to the right, you will see that the pixels actually change. I move it back, and I move it to the right again. Whereas on the dithering that is ordered and live on your Pebble, you will have stable patterns on the device, which is noticeable better. Now, if you have multiple bitmaps moving around, the effect is even worse. So here I'm trying to achieve that effect. You have 50% of gray and 2 objects interfering with each other. Once you do that offline, you'll have that effect. Flickering, I mean, it's just obvious. Once they are perfectly aligned, it's full black, or you don't see any effect at all. That one here is at runtime now, and you can see while they are overlapping, you have animated noise. That is the same diffuse effect we had before when I was explaining Floyd Steinberg. And then here at the bottom, look now, it's a perfect stable pattern for the individual objects as well as for the intersection. So I want to achieve that. And here again, the same effect for objects that don't move, and yes, it's in color. The one I'm now concentrating on is the one at the top left, an 8x8 ordered dithering based on a so-called Bayes matrix, where I'll use a lookup. And if you compare that, for example, to the Floyd Steinberg, you see all kind of noise, whereas, yes, you recognize patterns, but they are at least stable on the 8x8 dithering. Okay, so how can we implement that? So when we practiced that talk, the question came up, how do you store gray values anyway? How do you have that many pixels information at hand? Well, the trick is to concentrate on things that are expressible on the Pebble, like a gradient, like shadow, or simple objects. Think of vectors you render, and you don't use black or white, but you use real gray-ish colors. Now, when you have that, the question is, how do you render a single row, for example, efficiently? And this is what we are now doing. So I'm trying to use here, that's a quick recap. That was the ordered dithering algorithm, and it had at one point this find closest palette color based on the palette. Well, if we do that in black and white, we can dramatically simplify that. since we're only having two colors, we compare the pixel value to the threshold. And if we do that and it's larger, it's white, and if it's lower, then it's simply black. It's super simple. Now we have a Bayer matrix, and the only reason why everything is multiplied by 4 is I took it from another project of mine, and I was too afraid to multiply that and introduce any errors. So just think of it as literal numbers. And then the simple function I'm introducing here is I give you two coordinates. Think of it. You need the real target coordinate to find the right component of the matrix and the shade of gray, and you give me a G color. So that's a simple function. It's called color for gray. Now, what I'm trying to achieve is to render that gradient here as efficient as possible. I have the color for gray, and I'm now inside my layers update proc, right? Okay. I have two values. Yes, I could just hardcode white to black, but I think more flexible here. I want to animate the gray values in the end, so I have a gray value for the top and a gray value for the bottom. Okay. So the first thing I do is I loop over all the rows. I know, since I'm really doing here the window update proc, and I'm using the globals as before, as I said before, maybe the window size comes from somewhere else, as I see now. Yeah, I think I put it somewhere else, but then I'm iterating over all the rows, and inside a row, I mean, since we are doing a vertical gradient here, the gray value for each row is the same. I can compute it only once per row, and that is this expression here. Is it clear why that expression looks like that? Who can explain it here? Exactly. So that's nobody. I did that to avoid floats, right? Think of it. We are now doing some fragments or fractions of something, and I don't want to introduce floats. So a quick recap what I'm doing here. What I'm trying to achieve is a linear interpolation between two colors, and I'm going from one point to another point, and yet to another point. So when you look at the first point on that gradient, you are at fraction 0. You are at 0% of the whole height. Whereas now where we are at 25% of the total height. And I want to determine which shade of gray I have to calculate here. So that's pretty easy. I just say, well, you can do that just with your gut feeling, right? If you are at the 25% at the top, it's 75% of the top gray value and 25 of the bottom. And the formula here just expresses this. And I mean, it's super simple, and you can just, by poking with a few values, verify that that algorithm is right, or that expression. If you go to 75%, it will flip again. So 1 minus 75 will turn to 25% plus then 75%. In total, this 1 minus fraction plus fraction will always sum up to 1. So you will linearly interpolate between those two values. And what you see on the left-hand side is just that expressed as a formula, right? So we have the y coordinate, we have the height, we stored that in our local variable before. And then we express that formula here just not with explicit numbers, but instead with the values we have. Okay, so remember, I want to go to a version without any floats. And I certainly have a float here. Just look at the first line, it's a float, right? In order to do that, I multiply the whole expression here by h. So when I do that, 1 turns out to be h, and frac turns out to be y. And if I do that and multiply it by h, I got to that expression here. Now, since I multiplied it by h, I have to divide it by h again, in the end, what I do here. And now, again, mathematically, both expressions are equivalent, but you won't see any floats. All right, so this is that expression here. Now, what I have at this point is a linearly interpolated gray value for the row I'm currently working on. I'm iterating over every row, and I have the row gray for that specific row. Now, what I do next is I'm iterating horizontally over that very same row, and determine the color, the gray value for each pixel. We introduced that before. I put in the x and y coordinates since it depends on the coordinate. It's ordered. It has to look up in the matrix. and then I put in the gray value, which is stable for the whole row. And eventually, I call the graphics draw pixel, and that function has been there for ages. It's nothing new really here. Maybe for some of you it's new how to calculate that gradient, but really we don't talk about anything fancy new when it comes to API now. I recorded a video of that. So is everything here clear? Yeah? Okay. I recorded a video, and just in case that you wonder, is that a Pebble? Yes, that's a Pebble. This is how we program for Pebble. This is our, we call it Big Board 2. This is the board we are doing new firmware development, but also app development if we want to do enhanced debugging capabilities or anything. So think of it as a Pebble in an ugly case. Okay, but anyway, it's running the app we just developed, and you see here an animated gradient. Now, if I push that button, you'll see it can go way faster, right? I'm pushing the button again, and you see draw pixel. That is the algorithm we just implemented. And the other one uses the new frame buffer API, where we have direct access to the frame buffer. Now, you might think, it's not that much faster. Well, yes, it's faster, but not that much. Actually, the fast version, the frame buffer version, is not CPU bound. It's not that it cannot render faster. It's just that I trigger the timer at 30 frames per second. Whereas that one cannot catch up at all. The other one just runs smoothly. Now, we have these two new functions. And the idea is that instead of calling draw pixel or draw line or anything, we give you direct memory access to the frame buffer of your application. You can acquire or capture the frame buffer by calling graphics capture frame buffer, and you put in the context we have as an argument in an update proc, and what you get back is a G bitmap. And once you are done, you give it back. And the reason for that is, as long as you capture the frame buffer, nobody else can render to the frame buffer. That means when you call a draw pixel function while you captured the frame buffer, it does nothing, unless you release it afterwards. And it's your job to release the frame buffer. Okay, a quick recap what gbitmap looks like. Now that we have direct access to a gbitmap representation of the frame buffer, how does gbitmap actually works? Well, that's defined in Pebble H, again, forever, I think. And it's also explained in the API documentation, but just to be sure, I want to explain it here. So we have actually pixels on our screen. Say we have a gbitmap that is 29 by 5 pixels. We want to address pixels here. And say we want to address that white pixel there, which is at coordinate 9, if you start counting at 0, or 10, or what is it? 0, 1, I don't know. Actually, what we need is the offset to the byte in order to change that pixel, right? So what I do is I somehow have the byte offset of the very first pixel, and then I go to the right by the x coordinate divided by 8. Since we are only handling black and white pixels, that means per byte we are storing 8 pixels. And when I am at the 10th pixel, I need to go to the second byte, right? Okay, now where do we get the pointer to the first byte of the frame buffer from? Well, actually, that's in the gbitmap struct, the addr pointer. So I can store the bitmap's address in my byte offset, and then I add, for the horizontal shift, I divide the x coordinate divided by 8, have at least a column. Now, if I want to address the third row here, or the fourth row there, I also have to go down. And now, for optimization reasons, we have some padding, optional padding on the gbitmap. That means here, on the right-hand side, you see some gray area on that diagram here. We word align our bitmap. So whenever you have a bitmap that's only a single pixel wide, it takes 4 bytes per row. And also, if you have 33 pixels per row, we would need 8 bytes to store a single row. So you cannot simply multiply and offset and divide something with the x and y coordinate. You have to know how wide it is in bytes. And we have another field on the struct that gives you that information. That's row size bytes. and you simply multiply the y coordinate with that one here. That gives you the byte offset, but also be aware that we have a bounds property. So bounds is the physically visible pixels. So you can certainly access the area here, but it's never ever visible. And also bounds, if you look at grec's definition, can have an origin. So it is not guaranteed for every G bitmap that it always starts at 0, 0. And the reason for that is that we can have sub-bitmaps. In fact, there's an API call for that, sub-images out of, or sub-bitmaps out of bitmaps, where we share the same pixels, but start at a different offset. So when I'm talking about X and Y here, I'm always talking about the absolute X and Y, and you have to relatively look where your frame buffer starts. Okay, so that's GBitmap. My update proc now looks like that. At the very beginning, I'm obtaining the frame buffer, I'm capturing it, and then in the end, I release it again. And in between, I'm somehow messing around with pointers. I'm doing the loop again. So here, I'm looping over all the rows, and now look at the row pointer. At the very beginning, I'm storing there the top left pixel of the frame buffer. Then I'm looking at the origin and move that down by the origin multiplied by the row size bytes. And after iterating over each row, I'm adding that to the pointer as well. So whenever I am inside that loop, my pointer points to the first 8 pixels of that row, and it will go as wide as row size bytes. Does it make sense? Cool. Now, this one here is clear. We already had that, linearly interpolate per y coordinate. Now, here comes the trick. I'm now calculating not a gray for each pixel, but instead a dither pattern per row. Why is that? Well, remember the fact that we use ordered dithering, which essentially means for the same gray value, if you draw a horizontal line, the pattern repeats every 8 pixels, or every byte. That means all the bytes of a single row, when you do a vertical gradient, all the bytes per row are exactly the same value. All I have to do is calculate that byte once, and I'm doing that here. So I'm giving for a y coordinate just 8 different, so the 8 consecutive x coordinate values to store a single byte, return that, and that is my pattern for the whole row. And after I have that, I store it in row gray dither and use a single call to memset to completely blit that line. And now when I said that we for optimization reasons, we store the row size bytes, I totally take advantage of that here right now. So I don't care about any clipping or bound stuff here. I really just fill the whole bytes for that row, no matter if I'm writing to any invisible bytes here. In fact, I do. If you do the math, there are a few pixels that are invisible I'm writing to right now, but who cares? Okay, so that's the algorithm. Super simple. I'm making use of some qualities of the problem I tried to tackle, granted. But again, just to convince you, this is draw pixel, and that one is the direct frame buffer. Okay. So who is, thanks. Who is old enough to recognize that picture? Or comes from Europe or whatever? Okay.
Okay, I'm old.
Okay, me too. So that's, what is it?
I think it's the Amiga bouncing ball.
That's the Amiga boing ball. Do you know when it's been announced?
Before these guys were born.
Most of them. It's been announced at CES 1984, Winter CES, and it's been a tech demo to show how capable Commodore's, well, it was before Commodore, Amiga's hardware platform was. In fact, that demo here, it's only a screenshot, but what it does is it has a ball that rotates and bounces, hence, and it did some sound, hence the name boing ball. And in fact, it did no real 3D at all. It was all faking. Since it was a palette-driven and it had bit-oriented frame buffer, they could do a whole lot of tricks. And I thought, now that we have access to the frame buffer, why not port that to the Pebble? And that's kind of a cliffhanger for our third part. So when you look at it, this one here is a photo I took of the Pebble, and it uses all the techniques we saw before. So you see a vertical gradient here, and also you see order dithering. Yes, it's clearly visible, but I mean, you see it's going from white to black, and also that shadow here, how subtle it renders into that gradient. Now, when I was telling you that I used qualities of the problem I was tackling, doing the vertical gradient, you might think that, well, the frame buffer access is only useful for a single thing. Well, let me show you that. That's doable on Pebble. It's fully animated. It's changing the texture, and really,